Um, Hi everyone, I'm Muyiwa. For those of you that don't know me, I'm a sysadmin on the entity team working on CMP. And I'm going to talk about comprehending containers. It's basically a primer on Linux containers. So what's the talk about? Linux containers, obviously. What they are, how they work, what the problems that they solve for us, and what the alternatives are. So we start with the containers overview. Most of us must have heard about containers if you're working in Headtalks, because the entity CMP team that uses containers for pretty much everything. But you might not really understand what containers are if you don't work with them on a daily basis. So what are containers? They are kernel-enabled process user space isolation. So basically, you have processes running on your Linux machine. They are all controlled by the Linux kernel. And the container provides you the ability to isolate those processes from one another in a very transparent way using the kernel without any extra bits. It's also a method of software distribution and hosting. And it's also chroot on steroids. Chroot, or chroot, is a feature of Linux kernel which allows you to change the apparent root of your machine. And that's a feature that containers use. So it's just a way to describe it to someone that is a bit familiar with some parts of Linux but not familiar with containers. So the best way for us to understand what containers are is to look at a real-world analogy. So containers get their names from like other kinds of containers in the world. You have like, you know, the Tupperware containers and shipping containers and all those kind of things. So but we're going to look at the shipping containers as an analogy. Say you want to ship a couple of stuff. You want to ship a car, some beans, a piano, an iPhone, a bottle of wine, and a box of kittens. You want to ship all these things to some, you know, arbitrary location in the world. You need to figure out a way to package all these things in a way that they can be shipped and get to their location successfully. And you need to figure out a way to do that for each of them individually. And because they are all different kinds of items, they all have their peculiarities. Some of them are fragile and all that kind of things. So in a traditional method of shipping, you have to figure this out individually. But with the invention of shipping containers, all you have to do is figure out a way to get all these items into a container or into multiple containers. And once you've done that, then there is a separation of concerns. You no longer need to care about the individual items, but all you care about is the container itself and how to get it from point A to point B, and how it interfaces with other containers, and how it interfaces with the ship that is doing the transportation. So you get all these things into your container, and then it goes on the giant ship and it goes to its destination. And that's all you need to care about. So that kind of explains on a very high level what containers are all about. We can look at another analogy using a software. So assuming I want to set up a simple web server stack on a server, on a bare metal server, I have my operating system. At the bottom, I have my web server, I have my database server, and I have my scripts written in Python, Perl, or PHP, and then that makes up my web application. So I want to set this up, and there are three considerations that I can make on where to deploy this. So I can either deploy it on a bare metal server, I can deploy it on virtual machines or containers. And looking at the options for these first two methods would help us appreciate what containers bring to solve this problem for us. So the first option is with bare metal. So if you look at the little diagram in the corner there, you have the server layer at the bottom, which is a physical layer of the bare metal server. Then you have the host operating system, which in this case is Linux, and the libraries on top of that. And then you have your application on top of that, which is Apache or Nginx for the web server, and MySQL or Postgres or whatever other database application you want to use. Now, these database application and server applications are tightly coupled to the host application because they share libraries with the host. So that means you get a lot of advantages, but there are also issues with this. The advantage you get is bare metal performance. So you have access to the full resources of the host operating system, and there is no layer separating the resources of the host from the application. However, there are issues because the application, like I said, is tightly coupled with the host, so it's not easy to do a migration. If you need to move workloads from one server to another, there are issues there because the other server you want to move to has to have the exact same resources as the one you were coming from. That makes it not portable. And there are also issues with security and resource isolation because one application could use up all the resources of the host and then cause the other one to not have the resources it needs. So there are issues there, and that causes inefficient resource utilization. The second option is with virtual machines. We have the same two layers as we had in the previous one with the server and the host operating system. And then on top of that, we have a hypervisor. The hypervisor is a virtual machine manager which helps you to provision virtual machines and split up the resources of the host in order to emulate the host environment for guest operating systems. So on top of that, you have the guest operating system, you have the libraries, and then you have your application. So in this case, unlike with bare metal, the applications are decoupled from the host, and that makes them more portable so you can move your workloads across different hosts. But there are issues with this as well. So you can see it's decoupled from the host and it's portable, but there are issues with resource utilization because the hypervisor uses a considerable amount of resources from the operating system, and that kind of reduces the amount, from the server. That kind of reduces the amount of resources that you have available to your applications. And there are also issues with the kernels. Each virtual machine has a full operating system running in it, so it has its own kernel, it has its own libraries and everything. And that means that if there is an issue where you need to patch the kernel, you have to patch both the kernel on the server and then in the virtual machines as well. There is also the issue with performance overhead, like I mentioned. The guest operating system has its own operating system in there using resources that are not being used by your application. And the host also has the hypervisor, which is also using some resources that are not being used by your application. Your application doesn't end up using as much resources as it could. And then we have containers. So with containers, you have the same two layers again with the server and the host operating system. Or then on top of that, directly on top of that, you have your container. So your container is basically all the libraries and binaries that your application needs to work, and then your application bundled together. There is no layer of hypervisor separating them. They run on the bare metal, but in an isolated environment. So this gives us the best of both worlds. You get the bare metal performance, and you also get the isolation in the same package without really losing out in anything really. So you get the portability, so you can move the workloads. All you need is another server that has the same resources, the same operating system, which is basically a Linux kernel, and you can move your container from one place to another. So we also have the container engine there, which is doing something which we're going to talk about later on, so just ignore for now. So this gives us a kind of a overview of what I've been talking about. You have the bare metal, the virtual machines, and the containers, and that gives us an idea of the stack and how it all works. So how does this work? You know, we've seen, you know, how the stack is organized, but in reality, how does it work? Containers don't exist as a distinct construct in Linux. What that means is, if you go to the Linux kernel and search through the code, you're not going to find where the container code is written. But instead, containers are made up of different features of Linux combined together. So there are different features that the Linux kernel has that, when combined together in a certain way, can be used to create a container. So we're going to talk about just a couple of them. We have namespaces, which is workspace isolation, C groups, which is control groups, so resource isolation, capabilities, which is for access control, AppArmor SE-Linux, which is for security profiles. So C groups are control groups in the Linux kernel, and they are used to enforce limits on resources against specific processes. So if I have process A, which is my web server, Apache, for instance, running in a container, running on my server, if I apply a C group for memory for it, I can restrict the amount of memory that server can use while it's still running on the host in my server. So there are several types of C groups. There is the I/O C group, CPU, memory, networking, and so on. And all these can be applied either individually or together to restrict the resources that a single process can have while running on your server. Namespaces are process isolation layers in the kernel. So they provide a way of isolating different layers of the kernel from the process. So a good way to explain it is by looking at the types. So there, for example, you have the process ID namespace. So those of you that have ever used a container, if you log into a container and you check the processes running the container, usually you only have the process for your application, and that's running as PID1. But usually PID1 is only restricted to the init process for Linux. But that's possible because the process itself is not actually running as PID1 on the server, but it's running on its own isolated namespace, where as far as it's concerned, it's the only process in that namespace. So another good example is with the network namespace, where you can have your process running on its own completely separate network stack. It can have its own network devices, it can have its own firewall rules, it can have its own ports, other network resources running on the same server, but in a completely different namespace. So if you go on your server and you view network devices on that server, you're not going to see those because they are not in, as far as the Linux is concerned, they are in a separate namespace. And the process cannot view the resources of the host unless it is allowed to when it's isolated. Capabilities is an interesting one. It's a way for Linux to provide features that are normally restricted to a privileged user, to an unprivileged user. So usually you don't want to run a process as root. If you're running a web server, you don't want to run it as root, for instance. But you want the web server to be able to do some things that Linux typically doesn't allow a process to do unless it's root. For instance, a web server needs to bind to port 80 or port 443, but by default, applications are not allowed to bind to ports lower than 1024 unless they are run by root. So there needs to be a way to assign the capabilities for an application to perform those features without actually giving it full root privileges. So that's what capabilities does. That is why if you log into a container, you see that the container is running as root, but it's not actually the full root user of the Linux kernel, of the Linux OS, but instead is a user that has a limited subset of features that has been assigned to it. So that's just a quick overview. There are so many other things that are used to make up a container, but we just highlighting a couple of them that I think are important to know. So how does this all work at the end of the day? You know, these are, like I said, there is no containers feature in the kernel. So you bundle all these things we just talked about, and maybe you write a very long shell script, and then you have a container. But nobody wants to do that. That's very painful, and that's prone to errors. So instead, what do we do? Yep, that's pretty much it. We use container runtimes. So we use container runtimes to make life easier for ourselves. So basically, container runtimes, also known as container engines, that's what we saw in the diagram earlier that I told you to forget about. So container runtimes provide a way to abstract away all the features and complexities of the Linux kernel into a simple user experience with command line tools and API tools that you can use to provision containers for yourself. So the examples of containers, we have several. We have LXD, LXC, Docker, Rocket, and so on. They all provide the same functionality in slightly different ways. But Docker kind of has won out the race when it comes to container runtime, especially for application containers, because that's what is in use that's what's the most widely adopted in the enterprise and in general. So it provides several features that are nice on top of the default features that you get from the Linux kernel. For instance, it provides a repository system which you can use to publish containers and download containers, so you don't have to build yours all the time. You can just download one that has already been built by someone else and run it on your machine. And it also has a nice layered format using UnionFS, so you can layer you can use a different container image as a base and then add your own features on top of that and go on your way. It also has an easy to use and powerful API, which we use a lot on the CMP side of things. So there are two types of application containers that we have. We have the application containers, which is mostly what I've been talking about in the past couple of minutes. And those are containers that are basically built for one function, and that is to run a single application. So in the application container only contains all the libraries and binaries that it needs to run that single application, and that single application usually runs as PID1. However, you also have machine or operating system containers, and these try to mimic the features of virtual machines as much as possible. So they are a complete operating system environment, but they don't have a kernel in them. So they're still using the kernel of the host, but they have all the user space libraries that you would find in like an Ubuntu or a Debian virtual machine. But in this case, it's a container. So containers are awesome, and they provide a lot of features, and they do a lot of things for us, but they are not perfect. So there are a couple of issues with containers, most of which are currently being worked on, or at least being debated. And while it's unlikely, there's a potential that there could be a bug in a container that could cause a kernel panic. A kernel panic is the Linux equivalent of a blue screen of death that you see on Windows. And if that happens, usually if you're running a virtual machine environment, that's going to affect that single virtual machine, but it's not going to affect the rest of the host, because the rest of the virtual machines, all the hosts, because they all have their own standalone kernels. But with containers, there's a single kernel that all of them share. So if there's a kernel panic, it's going to affect the entire host and everything goes down. This is very rare, but it can happen. There's also the possibility of an attacker escaping the restrictions and the security of the kernel and of the container, and becoming a privileged user on the host, and doing all manner of crazy things. Most of the popular container runtimes have a lot of security features to ensure that this doesn't happen, though. There's also complexity when it comes to stateful applications, because containers are very nice for stateless. Stateless applications are basically applications that don't have any static data. So they are applications that you just start up, they do a thing, and then they write their data somewhere else, and then you can start them up and kill them as you like. But we don't only have stateless applications, we also have stateful applications like databases, like queuing systems and all that. So we need to care about the data for those applications. And we can still run those applications in containers, but then we have to care about where the data goes, so we need to mount in volumes and stuff like that. There's some complexity there, but again, most of this is being worked on already, and there are ways to use containers with stateful applications, which we currently do in CMP. So there are also some security implications with using third-party images, but that applies to pretty much anything. You don't just download anything off the internet that you don't trust. So containers versus virtual machines. If you've been paying attention to the talk, you realize that containers are very similar to virtual machines in the way they work, but they are not really similar at all in the way they are set up, or in how they actually work under the hood. So, but there's a lot of comparisons between virtual machine and containers, because a lot of times they are used for the same kind of workloads. So with containers, you have a single kernel. With VMs, you have multiple kernels. There are advantages and disadvantages to both approaches, but that's how it is. With containers, you have elasticity. So if I needed to spin up 5 instances of a web server on a single host, I can run a single Docker command and it does that for me. And it does that instantly within seconds or less. But with virtual machines, I can still do this, but it's going to take longer, and it involves a lot more inputs. It's also, the images for virtual machines are also much larger than containers, because containers can be very tiny. They only require just the libraries and the application that they need to run. So there's a lot less overhead with containers, and you have instant scaling with. So what are the alternatives to containers? There are 2 main ones that I could find. One is statically linked binaries. With modern programming languages like Go and Rust, you have the ability to build, or even Java, I think, has something like that. You have the ability to build a single binary that has all the dependencies in it, all the libraries and everything it depends on. So you have a single file which you just copy it somewhere, make it executable, and run it, and off you go. So that can replace some of the requirements for a container. However, it doesn't provide some other features that containers provide out of the box, like the isolation and the security and the other things like mapping ports and all those kind of things. So usually they are used in conjunction with containers, not as an alternative to containers. Another one is unikernels. Unikernels are quite interesting. They are kind of a way to build up a bootable image that has only that just only has what it needs to boot and to run a single application. So it doesn't have any library that it doesn't need to either boot or run a single application. So it's very, very, very lightweight, but it boots from bare metal. So it doesn't run on top of an existing operating system. It has the operating system in it. That's an emerging field that isn't really being used that much in production at the moment, but it's something to look at as an alternative to containers. So container orchestration. So I've decided I want to use containers. I've built a bunch of containers out, and I want to host my application in containers. Maybe I'll even have them in micros services. So I have like 50 microservices that make up my application. I need a simple way to host them, and containers provide this using container orchestration. So container orchestration enables workload scheduling, scaling, monitoring across a fleet of hosts. So if I have 10, 20 hosts in my data center and I want to schedule applications on different ones running on containers and all that, I can do that using container orchestration. Now this is a whole other field that will take another talk to even go a little bit into it, so we're not even going to try. But there are a couple of examples if you want to do the research. There's Kubernetes, which is the standard at the moment. There's Rancher, Docker Swarm, Docker Compose for single hosts, and all that. But this is another field of containers that provide a lot more control and a lot more power to us as administrators and also as developers. Thank you. So, any questions? Guess not. All right, thank you for listening. Oh.
Is there anything happening on the .NET side of things, Windows? Do they do anything like this? This is obviously very Linux.
Yes.
What's happening in Windows?
Yeah. Yes, there are. You can run Docker containers on Windows, but they are still Linux containers. The way it works is there's a very lightweight virtual machine layer on top of Windows that the containers run on. So it's kind of the way it works on Mac as well. So it's still Linux containers. But I know Windows is doing a lot of work. Microsoft is doing a lot of work to get like proper Windows containers, but I don't really know much about what's going on in that field. But I know Docker uses a virtualization layer to set up containers on Windows.
Yeah, I can understand that containers can be used on Raspberry Pis, for instance.
Yes.
Complicated one?
I think the problem is because the Raspberry Pi is an ARM platform, so whatever you're running on the Pi has to have been built for ARM architecture CPUs. So it's possible, but it's probably going to be a bit complicated. Although maybe if you can get an application, if you're building a container for an application that has been built for ARM, then you can write a Docker file and build it on Windows and have that running on the Pi. But the binary, the application that you want to run, has to have been built for the ARM platform. Yeah. You're welcome. All right. Thank you for listening.